each of the instruments play a different scientific role.
The near-infrared camera, or NIRCam, is the main imaging system.
One of the most amazing scientific tools of our time, the James Webb Space Telescope, has been helping us understand the secrets of the massive and astonishing universe, allowing us to witness the architectural progression of galaxies over billions of years. The James Webb Space Telescope has discovered a galaxy that shouldn't exist, and the newly acquired information gives insight into the unexpected elements the scientific community may have failed to notice. Skeptical, the scientists state that such a discovery is impossible and may go against what the known science principle has stated. What could this amazing discovery be, and what would the shape of the universe be altered? Join us as we delve into the galaxy that the James Webb Space Telescope detects that should not exist. The discovery of Pearl's DG. Among these unique occurrences is the recently discovered galaxy Pearl's DG, which defies models and predictions of galaxy formation and evolution. Pearl's DG isn't your typical dwarf. Galaxy is extremely uncommon and unusual, with several characteristics that set it apart. First, it is incredibly old and far away, having originated only 5% of the universe's current age, or 13 billion years ago. As a result, it is among the first galaxies to form in the universe's history and has seen some of the most significant and dramatic cosmic events, such as the reionization era. Pearl's galaxy is incredibly weak, with a luminosity of only 0.1% of the Milky Way, making it incredibly difficult to find and observe. When the earliest stars and galaxies ionized, the neutral hydrogen that filled the universe disappeared, making it transparent to light. James Webb discovered it by chance while studying a galaxy cluster. Astronomers working on the Pearls project in the NEP discovered a small, faint light source in the distance and deduced that it was a brand new galaxy that had never been observed before. Second, this galaxy is far from other galaxy groups or clusters. It looks like a lone island in the massive, empty universe ocean. Most galaxies are found in clusters where they interact and send reciprocal effects through the interactions of their radiations, gases, and gravity, making this very special. These interactions can modify the form and structure of galaxies, boosting or suppressing star formation, and even destroying or merging them. Contrastingly, Pearl's DG appears to survive and develop as an isolated system despite the continuous chaotic encounters. How did it manage that? Where did it start from in this extremely isolated corner of the sky? Some problems puzzle astronomers and call for further studies are listed below. Thirdly, this galaxy's structure and color composition are quite different from those of the other dwarf galaxies. This is why, mainly fashioned of old red stars, it has older stars with low mass, which are colder and longer lived than blue massive stars that are younger and cooler. It has extremely low metallicity and comprises few elements weighing more than hydrogen and helium, such as carbon, oxygen, iron, etc. They are formed when stars fuse nuclearly and are distributed across the galaxy and intergalactic medium by stellar winds and supernova explosions. A low metallicity suggests that Pearl's dark gas has remained pristine and primordial, with little star formation or feedback. This galaxy is particularly unusual and fascinating because of its highly irregular and asymmetric shape, which suggests that it has not been affected by tidal forces or collisions and has not developed a clear spiral or elliptical structure. Together, these features can shed light on the epic of galaxy assembly, AGN growth, and the first light in the universe. Using the JWST, astronomers discovered a dwarf galaxy they weren't expecting to find. It has no neighbors, is located roughly 98 million years away, and was seen in the backdrop of a picture of neighboring galaxies. Unusually for an isolated dwarf galaxy, this one has relatively little star formation activity. numerous findings suggest that the majority of solitary dwarf galaxies undergo star formation. The JWST's pearls, prime extragalactic areas for reionization and lensing science. Observing program's primary goal is to comprehend the first light, AGN expansion, and galaxy assembly epochs. It observed the CLG 1212 galaxy cluster as part of its investigation. The solitary dwarf galaxy known as Pearl DG was discovered incidentally. This discovery was reported in the recently published Astrophysical Journal Letters. The article is titled, "Pearls, a quiescent dwarf galaxy, possibly isolated and red giant branch tip distance, geometrical 30 mpc." The main author is Tim Carlton, an assistant research scientist at Arizona State University. Unlike large galaxies like our Milky Way, dwarf galaxies have significantly fewer stars than those galaxies. The exact number of stars in the Milky Way is unknown. In contrast, the most reliable estimates suppose that the upper limit is more like 400 billion. On the contrary, galaxies such as Pearls DG have a stellar population of almost 100 million. Pearls DG is distinctive in that it does not show star formations. The red giant branch RGB stars in the dwarf galaxy are luminous enough in JWST's detected wavelengths for the spacecraft to distinguish individual stars. One of the most distant galaxies where individual stars may be seen is Pearls DG. It is nearly too far away for the JWST to detect the stars. Studying the dwarf galaxy is considerably easier when individual red giant branch RGB stars are visible. Because RGB stars have a particular inherent brightness, the astronomers who made the finding can calculate the galaxy's distance, roughly 98 million light-years. They can also determine the star's ages, demonstrating the older stellar population in Pearls DG. Some stars would be substantially younger if they were still producing stars. The dwarf galaxy hasn't produced a star in at least 1 billion years, according to the researchers. The galaxy's absence of UV energy serves as some evidence. Pearls DG shows only weak UV radiation despite young stars releasing strong UV light. Researchers explain that we detect a very low SSFR, consistent with its low UV emission and the absence of emission lines in its spectra. This suggests that its star production stopped off over 1 giga years ago. A galaxy is referred to as quiescent when it stops producing stars. A quiescent galaxy has run out of gas needed for star formation. Usually, it results from an interaction between the inactive galaxy and another nearby galaxy that stops star production. Gas has either been removed from the dormant galaxy by the collision, or the gas flow has been disturbed. However, Pearls DG does not share any neighbors. Except for a small number of instances, these kinds of solitary, inactive dwarf galaxies haven't truly been observed previously. The fact that we see this object helps us enhance our theories for galaxy formation because, given our current understanding of galaxy evolution, they have yet to be predicted to exist, according to lead author Carlton. Dwarf galaxies that exist on their own are generally still forming new stars. Tidal stripping brought on by interactions with other galaxies can result in quenching. Other environmental impacts like strangling and ram pressure stripping can also occur. However, there are also further causes, the details of which astronomers are currently figuring out. However, the researchers claim the discovery of internal quenching mechanisms, such strong feedback, has been spurred by recent observations of many ultra-diffuse galaxies. Strong feedback from the largest and brightest stars can expel the gas necessary to form young stars. The authors use caution in their results, even if Pearls DG has no nearby neighbors. However, scientists note that it is impossible to fully rule out the possibility that previous contacts with other galaxies impacted its creation history. Nonetheless, Pearls DG's recessional velocity and luminosity distance support its inclusion in the Hubble flow, and no obvious indications of tidal interactions are present. Galaxies separate from one another as the universe expands because of the Hubble flow. Despite their expansion, Some galaxies interact with one another and even merge because of external influences. However, there's no evidence that anything that could have stopped the dwarf galaxy's star creation has interacted with it. Tidal forces cause galaxies to reshape themselves and can produce tails and streams of extended gas, dust, and star matter when they interact. However, Pearl's DG needs to exhibit these signs. This dwarf galaxy has a typical shape and is somewhat unremarkable. Dwarf galaxy. Compared to the Milky Way's approximately 200 to 400 billion stars, a dwarf galaxy is a small galaxy that is made up of 1,000 times more trillions of stars. It is also less massive, brilliant, and organized than the bigger galaxies. They often do not have a clear or elliptic structure and are asymmetric with no spherical texture pattern. Such galaxies dominate the universe and are mostly found in the clusters or groups that revolve around the more massive galaxies. Dwarf galaxies are very important for several reasons. They may associate or join each other to form more complex structures. Thus, they are the basic parts of the larger galaxies. Second, they can quickly turn their gas into new stars, producing massive bright stars that help enrich the galaxy with heavy elements, making them the sites of strong star formation. Lastly, they can also help us determine this mysterious material's features and distribution, which makes up 80% of the universe's total mass, so they are dark matter detectors. Astronomers can estimate the amount of dark matter that dwarf galaxies have, and how it influences their development by observing their motions and shapes, although the dark matter is invisible to the naked eye. Still, not all dwarf galaxies are created alike. Some are more peculiar than others. Some people place the Large Magellanic Cloud, estimated to have 30 billion stars and closely revolves around the Milky Way, among dwarf galaxies, while others think it is a regular galaxy. The concept is that the influence of larger galaxies plays a major role in the growth and operations of dwarf galaxies. Astronomers categorize dwarf galaxies into various subtypes according to their structure and substance. There is a belief that most galaxies, including dwarf galaxies, are like this composition and are due to the cooling of metal-rich gas or the intense interaction with dark matter. However, the Galaxy Evolution Explorer spacecraft operated by NASA detected new dwarf galaxies consisting of low metallicity gas. The Leo ring, a cloud of hydrogen and helium in the constellation Leo surrounding two huge galaxies, is where these galaxies were found. Due to their small size, the dwarf galaxies were observed to be given such an impact and lost apart by the nearby spiral galaxies, and star streams have resulted from this phenomenon. The local group harbors a lot of dwarf galaxies orbiting around massive galaxies like the Milky Way, Andromeda Galaxy, and Triangulum Galaxy. Based on a 2007 study, galactic tides can be the explanation that regulate the development of some dwarf galaxies when the Milky Way and Andromeda were young. Tidal dwarf galaxies are born when galaxies collide and their gravitational masses interact. Galactic tidal streams of stellar and dark matter halos are pulled from their parent galaxies. The research done in 2018 proposes that some of the dwarf galaxies in the neighborhood could have been present from the first billion years after the Big Bang, the Dark Ages. Astronomers believe Omega Centauri, the largest globular cluster in the Milky Way, is the core of a dwarf galaxy with a black hole at its center that the Milky Way once consumed. There are currently more than 20 dwarf galaxies known to orbit the Milky Way. The early universe. Until around 380,000 years following the Big Bang, the cosmos comprised a dense, opaque cloud of electrons and nuclei. The cosmos became transparent as the universe expanded because it cooled down enough to allow the plasma to condense into atoms. This light is known to us as the cosmic microwave background, or CMB. Unexpectedly, the temperature of the CMB is fairly constant throughout the sky. Generally, two objects must be in contact for their temperatures to be the same. But unless something else were happening to connect them, two locations on the CMB on different sides of the sky would never have been this close together since the Big Bang. Cosmic inflation is the most often accepted explanation for that something else. Quantum fluctuations caused the cosmos to inflate far quicker than the rate we see in later eras in the minuscule seconds following the Big Bang. The spots in the sky that are currently opposite would have been in contact before inflation, because the portion of the cosmos that became our observable universe was smaller than it seems today. Determining how inflation occurred and how to identify its impacts constitute a large portion of inflation study. For instance, gravitational waves produced by inflation may have left minute but detectable remnants in the CMB throughout the early universe. James Webb Space Telescope. The James Webb Space Telescope is an infrared astronomy space telescope. Its sensitive and high-resolution device allows it to reveal objects the Hubble telescope cannot find, as they are too dim, old, and distant. This brings about the capacity to perform studies on a wide variety of astronomical and cosmological subjects, like the earliest star observations, the formation of galaxies, and the detailed atmospheric characterizations of exoplanets that might be habitable. On December 25, 2021, Kourou, French Guiana, fired an Ariane 5 rocket carrying the Webb spacecraft. Its target, a solar orbit around 1.5 million kilometers from Earth, near the Sun-Earth L2 Lagrange point, was reached in January 2022. On July 11, 2022, the first image captured by the telescope was made public. Webb was designed and developed by the National Aeronautics and Space Administration (NASA) of the United States in collaboration with the European Space Agency (ESA) and the Canadian Space Agency (CSA). While Webb is operated by the Space Telescope Science Institute in Baltimore, Maryland, on the Homewood campus of Johns Hopkins University, telescope development was overseen by the NASA Goddard Space Flight Center (GSFC) in Maryland. Northrop Grumman was the project's principal contractor. The telescope bears the name of James E. Webb, the NASA administrator for the Mercury, Gemini, and Apollo programs from 1961 to 1968. Hubble's primary mirror has a diameter of 2.4 meters, but Webb's mirror is composed of 18 hexagonal mirror segments constructed of gold-plated beryllium. Together, these mirror segments are 6.5 meters in diameter. Webb's light-collecting area is approximately 6 times larger than Hubble, at about 25 square meters. Webb sees a lower frequency range, from long wavelength visible light red through mid-infrared, in contrast to Hubble, which observes the near ultraviolet, visible, and near-infrared spectra. To prevent the infrared radiation the telescope emits from interfering with the collected light, it must be kept extremely cold below 50 Kelvin. It is shielded from heat from the Sun, Earth, and Moon by a 5-layer Sunshield. In 1996, the telescope's initial designs began, dubbed the Next Generation Space Telescope. In 1999, 2 concept studies with a $1 billion expenditure and a possible launch in 2007 were commissioned. There were significant delays and cost overruns in the program. At a total cost of $10 billion, a significant redesign was completed in 2005, followed by years of rigorous testing and building completion in 2016. JWST feature. Compared to the Hubble Space Telescope, the James Webb Space Telescope weighs around half as much. Webb's primary mirror is a 6.5-meter diameter, gold-coated beryllium mirror composed of 18 hexagonal mirrors. The secondary support struts obscure 0.9 meters square of the polished area of 26.3 meters square, leaving a total collecting area of 25.4 meters square for the mirror. This surpasses by more than 6 times the collecting area of Hubble's 2.4-meter diameter mirror, 4.0 meters square. The mirror's infrared reflectivity is provided by a gold coating, which is protected from damage by a thin glass layer. Although Webb is primarily intended for near-infrared astronomy, depending on the equipment used. It can also view orange and red visible light in addition to the mid-infrared spectrum. It can identify objects from considerably earlier in the universe's history, back to redshift Z20, or roughly 180 million years after the Big Bang, and objects up to 100 times fainter than those detected by Hubble. In contrast, the first galaxies may have formed at redshift Z15, or roughly 270 million years of cosmic time, while the earliest stars are estimated to have formed between Z30 and Z20, or 100 to 180 million years of cosmic time. The furthest back Hubble can view is extremely early reionization, 400 million years of cosmic time, or roughly Z11.1, galaxy GN Z11. Additionally, objects in the solar system with an apparent angular velocity of less than 0.03 arcseconds per second and at an angle greater than 85 degrees from the Sun can be observed by Webb. This comprises comets, asteroids, minor planets in or beyond Mars's orbit, and the planets Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto, along with their satellites. Near and mid-IR sensitivity allows Webb to observe almost every object in the Kuiper belt that is currently known to exist. Furthermore, within 48 hours of a decision to do so, it can observe opportunistic and unplanned targets, like supernovae and gamma-ray bursts. Location and orbit of JWST. Operating in a halo orbit, Webb circles about the Sun-Earth L2 Lagrange point, which is located about 1,500,000 kilometers outside of Earth's orbit around the Sun. As it revolves, its actual position fluctuates between roughly 250,000 and 832,000 kilometers from L2, keeping it clear of the shadows cast by the Earth and Moon. For reference, the Moon is about 400,000 kilometers from Earth, while Hubble circles 550 kilometers above the planet's surface. This Sun-Earth L2 point allows objects close to it to orbit the Sun in synchronization with the Earth, maintaining the telescope's nearly constant distance and continual orientation of its equipment bus and Sunshield towards the Sun, Earth, and Moon. The telescope can simultaneously block incoming heat and light from all three of these bodies and avoid even the smallest temperature changes from Earth and Moon shadows that would affect the structure while maintaining uninterrupted solar power and Earth communications on its Sun-facing side. This is made possible by its wide, shadow-avoiding orbit. This configuration maintains the spacecraft's temperature below 50 Kelvin, required for feeble infrared measurements. Sunshield protection. Sunshield test unit stacked and expanded at Northrop Grumman's facility in California in 2014. Webb needs to be kept below 50 K to do infrared observations since the telescope's infrared radiation will overwhelm its instruments. Its proximity to the Sun and its sizable sunshield prevent light and heat from the Sun, Earth, and Moon. All three bodies are always located on the same side of the spacecraft because of Earth L2. By avoiding the Earth's and Moon's shadow, its halo orbit around the L2 point keeps the sunshield and solar arrays in a consistent environment. The precise alignment of the principal mirror segments depends on the stable temperature, resulting in the dark side structures. The sunshield consists of 5 layers, each as thin as a human hair, of Captain E film coated with aluminum on 2 sides, and doped silicon on the side facing the Sun to reflect solar heat into space. The telescope deployment in 2018 was further delayed due to accidental rips in the fragile film framework during deployment testing. The sunshield was made to be folded 12 times to fit inside the 16.1 9-meter-long and 4.5 7-meter diameter payload fairing of the Ariane 5 rocket. The intended dimensions of the fully deployed shield were 14.162 meters by 21.197 meters. Webb's field of view is limited to what is visible in its shadow at any moment. The telescope can view 40% of the sky at any given position, but it can see the entire sky over 6 months. Scientific instruments of JWST. The near-infrared camera, or NIR-CAM, is an infrared imager with spectral coverage spanning from the near-infrared 5 micrometer to the edge of the visible 0.6 micrometer. 10 4-megapixel sensors are present. The observatory's wavefront sensor, NIR-CAM, is necessary for wavefront sensing and control operations, which aim to align and concentrate the primary mirror segments. NIR-CAM was constructed by a team led by the University of Arizona, with principal investigator Marcia J. Rica. The NIR-SPEC near-infrared spectrograph does spectroscopy within the same wavelength range. It was constructed by the European Space Agency at ESTEC in Noordwijk, the Netherlands. Along with personnel from the Goddard Space Flight Center, Airbus Defence and Space, and the German cities of Ottobrunn and Friedrichshafen, Pierre Ferroet, École Normale Supérieure de Lyon, is the NIR-SPEC project scientist for the leading development team. 3 observation modes are available with the NIR-SPEC design: an R1000 multi-object mode, an R2700 integral field unit or long-slit spectroscopy mode, and a low-resolution mode using a prism. The grating wheel assembly mechanism is used to pick a corresponding dispersive element, prism or grating, and the filter wheel assembly mechanism is used to operate a wavelength pre-selection mechanism to switch the modes. Both methods are derived from the Infrared Space Observatory's successful ISOFET wheel mechanisms. The multi-object mode on NIR-SPEC enables the simultaneous observation of hundreds of unique objects anywhere in its field of vision, thanks to an intricate micro-shutter mechanism. Each of the 2 sensors has 4 megapixels. MIRI, mid-infrared instrument, measures mid to long infrared wavelengths from 5 to 27 micrometers. It has an imaging spectrometer and a mid-infrared camera. Under the direction of Gillian Wright of the UK Astronomy Technology Centre in Edinburgh, Scotland, and George Reiki of the University of Arizona, MIRI was created as a joint effort between NASA and a group of European nations. The MIRI's temperature cannot exceed 6 Kelvin. This cooling is provided via a mechanical cooler that uses helium gas and is located on the warm side of the environmental shield. FGS, or NIR-ISS Fine Guidance Sensor, near-infrared imager, and slitless spectrograph, led by the Canadian Space Agency and project scientist John Hutchings Hertzberg Astronomy and Astrophysics Research Center, is used to stabilize the observatory's line of sight during scientific investigations. The fine steering mirror is driven for image stabilization, and measurements taken by the FGS control the overall orientation of the spacecraft. Additionally, the Université de Montréal's René Doyon served as the main investigator on the near-infrared imager and slitless spectrograph NIR-ISS module, which the Canadian Space Agency provided for astronomical imaging and spectroscopy in the 0.8 to 5 micrometers wavelength range. While they are sometimes referred to as a single entity, the NIR-ISS and FGS have completely distinct functions. The former is a scientific tool, and the latter is an element of the observatory's support system. To observe dim targets, such as extrasolar planets and circumstellar disks that are extremely close to brilliant stars, NIR-CAM and MIRI have starlight-blocking coronagraphs. These findings cause astronomers to pause and reevaluate their theories about how galaxies evolve. However, it's conceivable that the JWST will discover more solitary and dormant dwarf galaxies. Things will become more apparent as more observations are made, and finally, an answer will be provided. More detailed analysis of the star formation history of Pearl's DG and the dynamics of Pearl's DG concerning its surroundings are needed to understand its formation history further, but this discovery suggests the possibility that many isolated quiescent galaxies are waiting to be identified, and that JWST has the tools to do so. Are you a space lover who wants to show off your expertise and secure your phone at the same time? With our JWST Tough Case for Samsung devices, explore the cosmos. The Cosmos Lab space-themed case combines the mystique of space with a sleek design and good durability, all to produce a surface that brings the wonders of the universe straight to your fingertips. Your phone is shielded from everyday use by its sturdy dual-layer casing, and the cosmic print makes it stand out in any crowd. You can easily access all the buttons, ports, and controls, immediately and quickly charge the case wirelessly without taking it out. To get yours now, click on the description box below. Thank you for watching. Let us know your thoughts on this galaxy. Don't forget to like, share, and subscribe for more videos like this.